Hello, everyone. Welcome to the lesson on Principles and Applications of Mechatronic Systems. I'm the lecturer, Liang Guangrui. Today we look at Chapter 4 Servo Control Technology, Fundamentals of Stepper Motor, Part 2. In the last lesson, we've learned the structure and classification of stepper motors and understood the working principle of stepper motors. Now let's get familiar with the technical indicators and performance parameters of stepper motors, because these indicators and parameters are the key basis for our stepper motor selection. First is the step angle, which refers to the theoretical angle at which the rotor rotates when a pulse is input. For a two-phase hybrid stepper motor, a typical step angle is 1.8 degrees or 0.9 degrees. The smaller the step angle, the higher the resolution of the motor. For example, a 0.9 degrees motor has a higher resolution than a 1.8 degrees motor. Moreover, the smaller the step angle, the higher the allowable starting frequency and running frequency, which is more suitable for high-speed precision control. Next is the step angle accuracy, which represents the deviation between the actual step angle and the theoretical value. Usually this deviation is within plus or minus 5%. The accuracy of step angle will affect the cumulative error of positioning. So in some high-precision devices, we need to choose a motor with an error within 3%. Furthermore, it is the maximum no-load starting frequency, which refers to the highest pulse frequency that the motor can start instantaneously in the no-load state. The unit is Hertz. Since the motor of the stepper motor has inertia, and it needs to overcome the maximum static friction force during the stirring process. If the pulse frequency is too high, the rotor may not turn to place before the next pulse will come, which will cause the problems such as step loss or stall. If the stepper motor needs to be started on load, then the frequency needs to be derated, usually 30% to 70% of the no-load value. When starting a high frequency, we generally adopt trapezoidal or S-shaped curve acceleration and deceleration control. Then it is the maximum no-load operating frequency, that is, the highest pulse frequency at which the motor can operate stably on no-load state. In practical applications, our operating frequency should be lower than this value, and a margin of about 20% of it should be reserved to cope with load fluctuations. There's also the parameter of holding torque, which refers to the maximum torque that the motor can maintain when it is stationary and power on. The unit is Newton meter. At low speed operation, the output torque of the motor is approximately equal to the holding torque. So the holding torque is a core index to measure the load capacity of the motor. However, it should be noted that as the speed increases, the output torque will gradually attenuate because the induced electromotive force will be generated when the stepper motor is running, which will lead to a decrease in phase current and moment. Therefore, when selecting a model, you must consider the torque frequency characteristics. Operating torque frequency characteristic is also an important parameter, which describes the relationship curve between output torque and rotational speed, pulse frequency, similar to the mechanical characteristics of AC motors. Figure 4.9 shows the torque frequency characteristic curve of a certain Model 57 stepper motor. When selecting the model, it is necessary to ensure that the torque at the operating frequency point is greater than the load demand torque, and a safety factor must be superimposed. For high-speed applications, you should prefer to choose the motors with relatively gentle torque frequency curves, such as closed-loop stepper motors or servo motors. Finally, let's look at size specifications. Common stepper motor models include 28, 35, 42, 57, 86 series, etc. For example, 57 to 76 means an outer diameter of 57 millimeters and a length of 76 millimeters. In the same series, the larger the motor size, the higher the output torque, but the corresponding power consumption and cost will also increase. Therefore, when selecting a model, it is necessary to match the mechanical installation space to avoid the situation of a small horse pulling a big cart, or over-design. Through today's lesson, we've mastered various technical indicators and performance parameters of stepper motors. These indicators and parameters provide an important basis for us to select stepper motors, so that we can select proper stepper motors according to actual application. That concludes this lesson. Thank you for listening. See you next time.